This is the final episode of the 7th chapter of the Crystal Clear Electronics videos. In this episode, we will test different transistors.
Hello and welcome everyone. While you are handling transistors, it's very important to know if they are actually doing their job properly.
For example, I have a bipolar transistor in my hand. How do I know if it works?
This is a very interesting question. We'll see how our multimeter can easily and quickly check the devices whether they have failed. During these measurements, it's important to measure these switches as independent components. Therefore, it has to be disconnected from everything because you will get false results for the measurement. So you will only need your multimeter and component which you would like to measure. It's practical to find the measured components datasheet on the internet at first in order to know what you should measure on each leg and what the wiring of the device is. Let's look at the measures for each component.
First, let's measure a bipolar transistor.
Within that, also check for a short circuit of the base output for an NPN transistor. We have to do this measurement by using the multimeter's diode measure option, so I will switch the device into this function. If you would like to decide whether there is a short circuit between the base and one of its terminals, the collector or the emitter, then at first you will have to find the pin assignment of the transistor. In case of BC546B, you will find the following. If this is completed, then you connect the red measuring cable to the base, the black measuring cable to the collector, the way the figure below shows it. Now I'm going to do it live. So I've connected the red wire to the base and the black wire to the collector. We're experiencing a value of 800 to 900, which is about right. If you can see a value of around 600 to 680, the forward voltage of a PN junction on the display, then your transistor's two terminals are proper, they aren't wrong. If the multimeter shows a very small or zero value, then probably there's a short circuit between the two terminals. If you see a value of 1 on the display, then there's a break between the base collector. In the last two cases, our parts are faulty. We do the same investigation between the base and the emitter, but now we connect the red measuring cable to the base, the black measuring cable to the emitter. This is what I'm doing now. So I put the red one in the middle, that's the base, and the black goes on the right, which is the emitter. Here again, we're seeing around 800 to 900, which is quite adequate. However, we've brought you a bad transistor as well, or rather, we have destroyed this transistor. Now we'll also measure what it is like to have a bad transistor. I'm gonna connect this one to the panel, and I'm going to measure this one as well. The red one to the base, and the black one to the emitter. In this case, the multimeter shows 1, and the multimeter shows also OL, or overload. From here, we can see that this transistor is not good, as the diode does not open in the specified range.
It's very important to always check your transistors before building a circuit. This will prevent a long troubleshooting process. How can we check the base emitter and the base collector short circuit of our PNP transistors?
If you would like to measure a short circuit between the base and other terminals of a PNP transistor, then it will be different the way we connect the black measuring cable to the base, the red measuring cable to the other terminals. From now on, the way we measure is the same as it was before. Don't forget that the pin assignment of PNP transistors can be different, so you need to find the pin assignment in its datasheet. Do this measurement at home.
And now, let's check the collector-emitter short circuit.
The measures are the same for the NPN and PNP transistors, but the pin assignment can be different. Our multimeter should be switched to the diode measure option. In our example, we will measure a collector-emitter short circuit using an NPN transistor. Actually, we would like to measure the connection between the collector and emitter terminals, so we have to connect our measuring cables to these two electrodes. In this case, we don't really care about the color of measuring cables. For example, let's connect the black measuring cable to the collector and the red one to the emitter. That's what I'm doing now. Let's see what we see, but first, I'll put the good transistor back in to measure this. In this case, the overload label is displayed or 1 on other instruments. If this is displayed, then there's a break between the collector emitter, which means that it's perfect. However, if it's 0, or the device shows a very small value, then unfortunately the two terminals of the transistor are shorted.
Now we can fully test the operation of bipolar transistors. Let's also look at the MOSFETs.
Let's start by measuring the resistance between gate source and gate drain. This measurement can be done with the multimeter's resistance measure option, so you have to switch the device to this state. The measurement can be done to both N-channel and P-channel MOSFETs as well. You've got to be careful because the polarities are inverse on these devices. In the example, I'll use the N-channel MOSFET. In the datasheet, look up the pinout again. The pin assignment of the MOSFET in my hand looks like this. From left to right, gate, drain, and source. First, we connect the two measuring cables of the multimeter to the gate and source terminals. I'll do the same as well. We can see that the multimeter is displaying overload again. If the ohm meter shows us overload or 1, then the device likely works. Inversely, if you get a measurable resistance, then it's sure that the FET is faulty, i.e. the gate has punched through. Now repeat the measurement between the gate and drain terminals as well, in order to find out if there's a punch through. In this case as well, if you're able to measure resistance between the two contacts, then the device can't be used for switching. So in resistance measurement mode, we measure the two outputs of the MOSFET, and in this case, the instrument also indicates an overload, so there is no punching through here either.
Now, let's look at another measurement procedure. Measure the conductance between drain and source in the open state of the FET.
During the measurement, you have to switch the multimeter to the diode measure option. Be careful not to touch the terminals of the device with your hand, because it will affect the result. Connect the negative pole to the MOSFET's source pin. During the measurement, this will stay unchanged. Connect the multimeter's positive cable to the drain of the MOSFET. In this case, it can happen that the multimeter will show a short circuit or a break. This depends on the state of the gate capacitor, which we don't know. Now let's discharge the gate capacitor with the help of your finger, like so. You touch the gate and the source terminals at once. If you're done with this, there should be a break between the drain and the source. I've touched this with the multimeter, and it displays OL or overload. This means that our MOSFET is working so far. Now, take off the positive measuring cable from the drain terminal and connect it to the gate leg. Wait a few seconds and carefully put it back to the drain terminal. You can hear that the meter reads close to 0, so in this case, we have a positive measurement, because if we get a short between drain and source, then our transistor is correct.
Jelen esetben egy kedvező mérési eredményt kaptunk, ugyanis hogyha rövid zárat mérünk ilyenkor a drain és a source között, akkor a tranzisztorunk az megfelelő.
And why is it like that?
When your positive cable was on the gate terminal, the gate capacitor was charged up by the small current of the multimeter, so the FET became open. After the displacement of the measuring cable, our device indicated conduction between the drain and source. And now let's look at a third measurement. We'll measure the diode between drain and source. During the measurement, we short-circuit the gate and the source terminals, and we have to switch the multimeter to diode measurement mode. Now I'll short-circuit the gate and source outputs, the two end legs. The multimeter is in diode position. In this measurement, we have to measure a break, which I will do right now. That's correct. The reason for this is that we don't charge the gate capacitor because of the short circuit, so the FET isn't open. In case of connecting the drain source properly, current won't flow, i.e., you can consider it as a break. Let's replace the measuring cable. We connect the red cable to the source and the black cable to the drain. In this case, we should see a value of around 500 to 600 if it works properly. The reason for this is that the gate capacitor is not charged up again, so the FET isn't open. We have changed the drain source voltage levels. If you remember, previously I mentioned the body diode in the MOSFET, which will conduct in case of inverse connection. We presented this phenomenon and you successfully managed to measure the body diode. The question can arise, why do we measure the faults this way? The answer is that in all cases, we start from the internal structure and the expected operation. For example, we measure whether a PN junction, or body diode, the expected value of 0.6 volts falls and leads only in one direction. We can test if it actually opens a MOSFET, and if there has to be a break somewhere, then there really is a break.
And what can we do if the component is faulty?
If you don't receive the expected result during one of the measurements, even after multiple tries, then the component is faulty. In this case, carefully and immediately place it selectively in electronic waste bins, because it will only give you a headache if it doesn't produce the expected behavior later. This is the end of our work together. I'm glad I was able to guide you through your studies, and I hope I've made it easier to understand the switching devices. I wish you good luck for the rest.
If you like the topic, give the video a like, subscribe to the channel, and most importantly, build the circuits at home and read the written material. Below, you will find all the links you may need.
Join us next time and see you in the next Crystal Clear Electronics video. Bye!
Bye!